In this presentation, we will introduce to you the topic, have a literature review, present our results and discussion, and finally, conclude and recommend our project for further advancements. Okay, let's take a look into the introduction. Aluminum is a lightweight alternative to steel and is a very prevalent and crucial raw material for everyday usage. With the increasing demand and depleting reserve, recycling aluminum is prioritized to preserve primary raw materials. As an aging country, automation is highlighted as important in Malaysia to reduce hard labor. On to problem statement, cost and time to recycle aluminum has been a challenge. Therefore, few scholars has contributed in designing an automated collection robot, but a research gap is present where there lack any design that integrate detection, collection, and transport all at once. To overcome this gap, we delve into our objective, which is first, to create automated aluminum can waste collector that is capable of detecting, collecting, and transmuting aluminum. Second, to enhance the system by allowing it to detect excess weight in the storage unit and alert the user. In this project, multiple sensors such as load cell, ultrasonic, proximity sensor, actuator, motor, LCD display, and software will be used to achieve the objective and capabilities of the proposed design, which is traversal, obstacle avoidance, detection, collection, and weight quantifying and display, and finally, alerting the user.
Now we go on to the literature review section. So on our first literature is the PLC. So PLC is an industrial automation device that can execute logic control for machinery, processors, and systems based on program instructions. They are basically microprocessor devices that are used in industry to control plant operations. The input device that they can process are push buttons, switches, and sensors, and the output device that they produce are relay, signal devices, and motors. So the PLC can be written in a form of ladder diagram, which is a graphical language resembling the electrical relay diagrams. The figures shown on the slide is the diagram that are used for the ladder diagram. Second literature is the sensors. So there are three sensors that are going to be implemented for our waste collector robot design. We have ultrasonic sensors, inductive proximity sensor, and load cell. So the ultrasonic sensors are used for detection on any obstacle present in the path for the robot. Secondly, we have the inductive proximity sensor, which can detect metal within a proximity range between the robot and the metal. And lastly, we have the load cell, which is used to measure the weight of the metal aluminium can that the robot has collected. So it will measure the weight and it will signal to probably an output such as LED, LCD, and display the weight that the robot has collected. On to our third literature, Arduino UNO. Arduino is an open source electronics prototyping platform that simplifies programming, and it supports programming languages such as C, C++, and Python. Arduino is equipped with microcontroller that controls electronic devices such as sensors, actuators, buzzers, and hardware components. And it functions as a central processing unit which processes input and direct corresponding response to connected output components. Basically, we are going to use Arduino as the central processing unit for all the devices connected on our robot system. And our last literature is the components and outputs for our system design. We have the DC motor, buzzer, LCD display, and linear actuator. So these four components are going to be implemented to our system design, and it serves as the output for our robot. So the DC motor utilizes magnetic fields generated by the electrical currents to drive the movement of the rotor that are fixed within the output shaft. And then we have the buzzer, which produces sounds when voltage applied, used for alerts, alarm, notifications, and audible feedback in electronic devices. So in our case of our robot design, the buzzer will notify user that the waste that the robot collected has exceeded its capacity. Next, we have the LCD display with a flat panel display technology that relies on liquid crystal for operation and display input process as an output. And lastly, we have the linear actuator, which is it transforms rotational motion into linear motion, facilitating lifting, dropping, sliding, or tilting fast. So next, we go to the first part of the methodology, which is system modules and components. So here we have a table of the components that are used for our circuit board. So this table consists of components, devices that are used to operate our robotic system. So our first component, we have the Arduino UNO, which will be installed only one item. And then we have the battery for power source purposes. Next, we have the motor, which operates as a wheel for the robot. And next, we have the LCD, which for display purposes, and also LCM for display purposes also, and provide display interference. Next, we have the piezo buzzer with wires, which serves as the notification that produces sounds for the user. And we have the inductive proximity sensor, which detects the presence of metal. Next, we have a spark fun load sensor that measures the weight of the robot's trash can weight it has collected. And also we have the spark fun load cell amplifier, which read the changes in the resistance of the load cell, so they are directly connected. And we have the motor driver that controls the electrical current motor, so it basically just a driver for the motor to operate. And we have the bipolar stepper motor that functions as a linear actuator in the hands of the robots. And lastly, we have the push to off buttons for emergency override purposes. Now we go to the sequence of events of our robot system flow. So we have the flowchart of our robotic system. So when the robot is turned on, The DC motor that moves the motor and all sensors in the system will be turned on, meaning that the robot can move around and fully operational. As the robot is moving, the ultrasonic detection is also activated. So the ultrasonic will be the eyes for the robot, and if there is an obstacle in range, if the obstacle is less than 30 centimeters, the robot will stop moving, meaning that the motor will be shut off. And if the obstacle is more than 30 centimeters, which means that the robot cannot detect the obstacle, the robot will operate as usual. So once the robot stops, the inductive proximity sensor will do its work by sensing if there is a trash can near the robot. And if there is a metal aluminum trash can within its range between the robot and trash, the actuator will be activated and collect the trash. If it's not an aluminum trash can, the robot will ignore and proceed moving in another direction. After that, after the robot detect metal trash can, the load sensor will display the weight of the trash collected through an LCD display. So if the weight has not reached 200 grams, the robot will continue operating and display the current weight of the trash, meaning that, for example, if the robot only collected 5 trash cans and the weight is probably like 20 grams, so the robot will only display 20 grams. And if the weight reached its maximum capacity, which is 200 grams, it will display the 200 grams, and a buzzer will be activated indicating that the robot has reached its maximum capacity, and it will automatically stop operating. And finally, a stop button is available for emergency override, so the user can have the free will to turn off the robot at any time.
So now let's proceed to the chapter 3 methodology. So in this chapter, I'll explain about the system modeling that we use to design. We use a software called Freezing to design our circuit due to its comprehensive library of electronic components. And for our microcontroller choice, we're utilizing Arduino Uno, which is versatile and widely used and able to handle multiple input and also output. So for sensor, we have 3 different types of sensor used for our project. First is the inductive proximity sensor, where it's used to detect presence of aluminum can. And next we have a load sensor, which is used to detect a weight of the aluminum can that is being collected. And lastly, we have another sensor called ultrasonic sensor, which is to measure the distance from the robot to the obstacle in front of it. We have also a piezo buzzer, where it will turn on when it detects a load more than 200 grams. So for our movement and actuation, we're utilizing 2 DC motor for our movement, where it's powered directly to the Arduino board of 5 volt, and this motor is responsible for navigation control of unit for movement. And also we have here is a stepper motor, which is function as a linear actuator for lifting the aluminum can, where it's powered independently using 9 volt battery. So this is due to power segregation and also to protect the circuit from overcurrent. And next, for user interface and feedback mechanism, we also utilizing LCD with backpack IC2, where it's used to reduce the number of digital pin required. Therefore, utilization of Arduino able to be max. So the LCD will display the current weight of the aluminum can, and also same as the buzzer, which provide feedback for overweight. For safety measure, we utilizing a push to stop button to stop all of the motor movement in case of an emergency of malfunction. So for the next slide is the circuit diagram for our project electrical connection, where it's represented as a visualization for our overall circuit. So this is the Arduino board. On the bottom side is the digital I/O pin, while the upper one is the analog I/O pin. So for sensors and motors, it's using the digital I/O pin, where it's required for controlling on-off signal characteristic and also pulse width modulation to control the motor driver, where we use the digital pin to ensure that it's precise and responsive, where it's crucial for real-time response, especially related to movement and actuation. So for the analog pin, we use 2 components. First, which is buzzer, where it can generate different tones, and for the LCD, it's due to that we're using the I2C interface, where it's connected at this pin, where it's essential for the data transfer protocol.
In this slide, we will talk about the block diagram. The automated aluminum can waste collector block diagram, as shown in the figure, illustrates the operational flow of the system. It all begins with the start block, initiating the process, followed by a central control unit represented by Arduino microcontroller. When aluminum cans are detected in the collection area, the integrated load sensor within the Arduino recognizes their presence and triggers the subsequent actions. An essential part of the system is the actuator, connected to a motor, responsible for physical movement and facilitating the collection process by activating the cans. Precision sensors like ultrasonic sensor ensure accurate handling during collection, while the inductive proximity sensor helps locate the cans efficiently. After the collection process, the system provides the feedback through a weight display unit, showing the weight of the collected cans. This comprehensive setup ensures an efficient and effective automatic aluminum can waste collection process.
So I'll be explaining the ladder diagram of the PLC system of this project. So we'll be utilizing the PLC feeder system, and first I will be explaining about how the ladder diagram works, and after that we'll be showing you a simulation of the ladder diagram. So let's get into it. So for the first round, when the start button is pushed, the motor will be activated and it will be continuous run because of the latch, and it will run until the ultrasonic and inductive proximity sensor has detected any aluminum can around the robot. So for the second round, when it detects any aluminum can, the actuator will be activated and the actuator will pick up the aluminum can and it will put into the bin. So when the actuator is on, the alert cell will be activated, and because of the output is activated, the load cell function, normally closed in the second round, will be cutting off the actuator, the current flow in the second round. So the actuator will be deactivated and the load cell on the next round will activate the display function, which will be displaying the weight that has been measured by the load cell. So it will be keep showing the weight because of the latch, and it will also cut off the current flow in the third round so that the load cell is deactivated. So on the next round, the display we activate back the motor, and then the motor will continue the cycle of this robot back into the first round. The motor will be deactivated only if the ultrasonic and inductive proximeter has detected any aluminum can. So the flow will be repeated until the weight input by the load cell has detected the weight above the weight limit. So he put here is 200. So when it detects when the weight limit is above 200, when the weight input is above 200, it will connect the current flow inside this round and the buzzer will be turned on. So when the buzzer is turned on, the motor will be deactivated because of the normally closed switch here, and the buzzer will be kept running on until top button has been pushed. So when the stop button has been pushed, the buzzer will be deactivated and also the motor. So that's somehow how this robot works. So let's see how the simulation works for this project. So the stop button is activated, the motor is on. So when inductive proximity sensor detect any aluminum can, the actuator and the load cell will be activated, and after the actuator put the aluminum can into the bin, it will show the load cell will detect it and it will show the value inside the load cell in the display. So the display will show the weight and the motor will be activated to resume the movement of the robot until the weight input here is exceeding the weight limit. So when it exceeds the weight limit 200, we can see the buzzer is turned on. So to turn off the buzzer, the stop button will be pushed. So the robot will be resetted and the start button can be pushed back to restart the robot. So that's how this PLC works.
In this slide, we'll talk about the business and economic considerations surrounding our innovative automated waste collection project. These factors are crucial as they encompass a wide array of variables that impact the project's real-life applications. Let's delve into some of the key commercial and financial aspects that are pertinent to the success of our prototype and in practical settings. Firstly, let's talk about the operational efficiency and cost reduction. The implementation of the automated waste collector paves the way for significant operational cost reducing by optimizing the collection process, thus reducing the need for manual labor. By integrating sensors akin to those in our prototype, we can effectively identify and gather aluminum cans, minimizing manual interventions and leading to substantial labor cost savings. This streamlined approach not only enhances operational efficiency but also contributes to significant financial savings. Next, let's consider energy efficiency and sustainability. It's imperative to factor in the power consumption of system components like motors and sensors when designing an automated garbage collector. Opting for energy efficient designs ensures the system remains economically viable while also reducing its environmental impact, ultimately leading to long term cost savings. By utilizing energy efficient motors and minimizing energy consumption during the collection process, we not only lower operating costs but also align with sustainability goals, underscoring the importance of energy efficiency in waste management system. Moving on to risk mitigation and insurance implications, the adoption of an automated garbage collector not only streamlines waste management procedures but also reduces potential hazards associated with manual handling. With fewer manual interventions, the risk of mishaps or malfunction during collection is significantly reduced, resulting in lower insurance claims and improved overall safety. This enhanced waste management system not only make workplaces safer but can also lead to better insurance terms for businesses, highlighting the economic benefits of prioritizing safety and risk mitigation. Lastly, let's touch upon the maintenance cost and longevity. Regular maintenance is crucial for ensuring the longevity and optimal performance of automated waste collector. The integration of sensor provides a real-time data on collection performance and system conditions, enabling informed decision-making regarding maintenance schedules. This proactive maintenance approach, guided by insights from sensor data, helps prevent costly breakdown and ensure system operates at peak efficiency over time. By implementing preventative maintenance strategies and selecting reliable components, companies can reduce overall maintenance costs and extend the lifespan of their automated garbage collection systems. The focus on operational efficiency, energy efficiency, risk mitigation, and maintenance strategies underscores our commitment to creating sustainable and effective waste management solutions that not only benefit businesses but also contribute to a cleaner and safer environment for all.
So let us proceed to the next slide, which is the cost analysis. So in this slide, the total cost of development and assembly of the automated can waste collector prototype is around 836 ringgit and 90 cents. While the expense of creating the prototype is reasonable, the high cost is mainly due to the fact of the expenses of the motor driver and also the Arduino itself. However, this is only the prototype. Nevertheless, the actual cost may also exceed the prototype cost depending on the quality and quantity of the component used. But if we were to reduce the cost, maybe we can use a different alternative which is cheaper, but it's not guaranteed the quality and performance of this robot.
To conclude, this project has tackled the challenges of aluminum recycling, particularly focusing on secondary aluminum derived from used cans. While aluminum boasts advantages such as being lightweight and efficient, cost has posed a persistent challenge. Existing garbage recognition and collection systems have their limitations, often lacking mechanisms for efficiently handling garbage or falling into prioritized aluminum cans. To overcome these hurdles, our project introduces an autonomous robotic system designed to intelligently detect, collect, and transport aluminum materials for recycling. We've integrated a programmable logic controller (PLC) into the system to enhance accuracy and efficiency. Our primary objectives revolve around creating an automated aluminum can waste collector and implementing weight detection capabilities in the storage unit. By synergizing technology, environmental consciousness, and streamlined recycling practices, this project contributes significantly to sustainable waste management while advocating for aluminum as an eco-friendly material. Together, we're not just addressing challenges but also paving the way for cleaner and greener future. As we reflect on the project's overview, there are several key recommendations that can further enhance the efficiency and effectiveness of our automated waste collection system. One critical aspect involves integrating additional sensors such as encoders or gyroscope to achieve precise localization and navigation. These sensors provide valuable data for mapping the robot's surrounding and ensuring accurate movement within the collection area. Moreover, optimizing the robot's movement through the investigation of path planning algorithms can result in more effective collection procedures. By implementing advanced algorithms, the robot can navigate the complex settings with minimal travel time and energy usage, leading to improved overall performance. Looking ahead to future developments, upgrading to a more sophisticated microcontroller like the Arduino MEB4062 will be advantageous. This enhanced hardware will make it easier to integrate more sensors and apply sophisticated algorithms, ultimately leading to a more reliable and effective robot performance. Another important development involves the adoption of more economical and alternative components. Exploring and integrating cost-effective alternatives for various system components can significantly reduce overall expenditure associated with system procurement and maintenance. These cost-effective alternatives contribute to optimizing financial sustainability while maintaining system functionality. Lastly, creating a user interface and interaction is crucial to providing a user-friendly experience. This includes implementing an easy-to-use interface for scheduling collections, settling collection schedules, and monitoring system status. Incorporating buttons or touchscreen into the system can greatly improve usability, enable users to engage more effectively and manage tasks related to collection waste. This user-centric approach ensures total user satisfaction and guarantees a seamless experience with the system. That is all for our presentation. Thank you.